Imagine a future in which humanity not only leaves Earth behind, but settles throughout our solar system and beyond, transforming forbidding worlds into new spheres of life, culture, and discovery. Picture explorers forging an existence on the tortured terrain of Venus, forging domed cities above the simmering plains of Mars, tunneling beneath the frost-bound crust of icy moons, and even launching generation ships into the interstellar void. Such bold visions have, in some form, always been part of our collective imagination, from the earliest science fiction tales to the modern era of rocket engineering and exoplanet detection. In approaching these scenarios, however, we confront profound questions about survival. How to withstand the brutal heat of a runaway greenhouse atmosphere, how to endure decades of sub-zero nights, how to navigate radiation-blasted voids between stars, and how, in the far future, to push beyond our galaxy's rim. What follows is an expanded and unbroken reflection, an epic meditation, on how humans might meet these challenges and transform what once seemed impossible into a lived reality. For millennia, we gazed at the sky with little more than curiosity, charting constellations and weaving mythic stories of cosmic hunters or God's chariots. The Enlightenment brought telescopes capable of glimpsing the phases of Venus or Jupiter's swirling storms, hinting that these wandering lights were distinct worlds. The 20th century saw a sudden leap. Rockets that could breach Earth's gravity well, sending satellites, animals, and eventually humans into orbit. The moon landings, though short-lived, reconfigured our sense of possibility. The International Space Station, orbiting some 400 kilometers above Earth, came to symbolize a permanent, if fragile, foothold in microgravity, hosting rotating crews who glimpse 16 sunrises per day. Meanwhile, robotic probes like Voyager, Pioneer, Galileo, Cassini, and New Horizons ventured into deep space, sending back postcards of alien realms we had only dreamed of. Their data confirmed that reality is no less astonishing than fiction. Methane seas on Titan, subsurface oceans on Europa and Enceladus, monstrous storms on Jupiter, ring systems beyond Saturn's main set, and the surprising geological activity on Pluto. Yet, despite these triumphs, the full scale of cosmic distances became apparent. Even traveling at tens of kilometers per second, a velocity unthinkable in prior centuries, it would take tens of thousands of years to reach our nearest star, Proxima Centauri. The promise of colonizing new worlds remains overshadowed by the sheer immensity of cosmic space and the relentless hazards that stand in our path. Nowhere is that hazard more apparent than on Venus, often called Earth's sister planet, though this is a label of ironic contrast. With a diameter close to Earth's, Venus outwardly appears as a bright, cloud-shrouded orb in our morning or evening sky. But beneath those clouds lurks an inferno. Carbon dioxide composes the bulk of Venus's atmosphere, producing a greenhouse effect so potent that surface temperatures stabilize around 465 degrees Celsius, 869 degrees Fahrenheit, hot enough to melt lead. The atmospheric pressure is about 92 times that of Earth's sea level, roughly what a submarine might face nearly a kilometer underwater. Clouds of sulfuric acid swirl overhead, corroding metals and devouring unprotected instruments. Soviet Venera probes that landed on Venus in the 20th century survived mere minutes or hours at best, sending back fleeting snapshots of a scorched, rocky terrain. Despite these extremes, we can imagine future colonists harnessing advanced materials to create dome-like enclaves. Perhaps specialized ceramics or metals woven with carbon nanotubes could form the outer hull, able to reflect or radiate away the monstrous heat. Inside, engineers might deploy powerful refrigeration loops using energy from the intense sunlight that Venus receives, about double what Earth gets, converted into electricity by robust solar panels. Layers of gas or water stored in specialized compartments could serve as buffers, channeling internal coolants or deflecting external acids. Venus's thick atmosphere might also open the possibility for cloud cities that remain aloft around 50 kilometers up, where temperatures drop to a range more manageable for Earth-like engineering. Such airborne colonies, proposed in some NASA concepts, would float using the principle that breathable air, a mix of nitrogen and oxygen, is less dense than Venusian carbon dioxide at those altitudes. Colonists aboard these floating stations might look down upon the swirling acid clouds and the red glow of a surface in permanent twilight. Meanwhile, robotic rovers specialized with tungsten alloys and advanced coolant systems might descend to the blazing ground for occasional resource extraction, returning precious metals or data about planetary geology. For day-to-day life, colonists would remain in pressurized suits or behind sealed walls, stepping out into the swirling gloom only when fully prepared for the scorching extremes. Over centuries, it's conceivable that pockets of human civilization could transform the planet's deadliest traits into a harnessed resource. Vast solar flux feeding a robust power grid, carbon dioxide recast as raw material for manufacturing. In that far future scenario, what was once a literal hellscape might become a testament to the might of human adaptation. Shifting to Mercury, we encounter a planet that is, in many ways, simpler yet no less dangerous. Without any substantial atmosphere, Mercury's surface is bombarded by meteoroids and hammered by radiation. Its day spans about 176 Earth days, meaning a single sunrise leads to weeks of intense illumination and scorching surface temperatures near 427 degrees Celsius, followed by equally long nights of bone-chilling cold, dipping to around minus 180 degrees Celsius. Mercury also lacks the thick greenhouse effect of Venus, so heat does not linger into nightfall. NASA's Messenger spacecraft revealed that Mercury's poles, permanently shadowed in certain craters, contain water ice. This alone stirs the imagination of building outposts near those polar shadows, exploiting water for life support and oxygen. It's plausible to erect a Terminator base, perched precisely on the dividing line between day and night, constantly shifting over time, requiring the base to move or to exist in a carefully orchestrated zone that experiences near-perpetual twilight. Structures might utilize metamaterials that actively shift their reflectivity or conductivity depending on which side of the planet's environment they face at a given moment. Coupled with advanced battery systems or nuclear power, Mercury colonists could manage extremes by gathering solar energy during the day and releasing stored heat at night. Protective bunkers might extend below ground, insulating inhabitants from severe radiation bursts and meteorite impacts. Daily routines would be meticulously planned, with rovers scouring the crater floors for ice or metals, returning quickly to airlocks that are heavily shielded. Over time, Mercury's rich iron content might fuel a local manufacturing industry, forging high-quality steel from the planet's resources. Perhaps Mercury becomes a specialized center for building starship components, launching them outward via solar-powered mass drivers that fling cargo into orbit. Though living there demands unwavering caution, Mercury's extremes offer the lure of abundant solar energy and accessible raw materials. Mars stands apart as the object of near-universal fascination. It's remote enough to challenge us, yet close enough to remain in constant conversation among scientists, entrepreneurs, and dreamers. The red planet's thin atmosphere, mostly CO2, offers scant protection from cosmic rays. Average surface temperatures hover around minus 60 degrees Celsius, though midday at the equator can reach a tolerable 20 degrees Celsius. Dust storms occasionally sweep across entire hemispheres, blocking sunlight for weeks. Still, with each new rover mission, Pathfinder, Spirit, Opportunity, Curiosity, Perseverance, our understanding of Martian soil, climate, and water ice expands. One can envisage an underground labyrinth of pressurized modules, connected by tunnels bored through basaltic rock. The overhead regolith forms a natural radiation shield. Within these subterranean vaults, LED-lit hydroponic bays supply fresh vegetables. Water is recycled from the planet's ice deposits, and oxygen is extracted via electrolysis. Energy might come from nuclear reactors, from solar arrays that must be periodically dusted off, or from imported fusion systems once the technology matures. The low gravity, at just 38% of Earth's, would require colonists to engage in daily exercise or live in rotating habitat rings that simulate stronger gravity. Cultural life might thrive in these enclaves, with Martian residents developing their own art, architecture, even dialects. Some might propose eventual terraforming, introducing greenhouse gases to thicken the atmosphere or traveling farther outward. The gas giants present realms we cannot directly colonize, but their moons attract intense interest. Jupiter, the behemoth, with a diameter over 11 times Earth's, is an immersion in tumult, lightning-laced storms, swirling belts of red-brown ammonia clouds, and lethal radiation belts that would fry unshielded electronics. Its moon system, however, is a miniature solar system in its own right. Io is racked by extreme volcanism, while Europa's smooth, cracked ice shell hints at a vast subsurface ocean potentially teeming with microbial life. Ganymede is the largest moon in the solar system, complete with an intrinsic magnetic field, and Callisto orbits far enough from Jupiter's main radiation belts to be comparatively safer for human habitation. A large outpost might take shape in Callisto's craters, using thick layers of ice and rock as structural and radiation shielding. Over time, nuclear reactors or advanced solar arrays could supply power. Meanwhile, robotic submarines on Europa might drill through kilometers of ice to explore the hidden ocean. If the ocean is proven to hold life, perhaps in the form of microbial mats around hydrothermal vents, the entire question of cosmic biology changes. Humans stationed on Ganymede might develop beamed power networks or coordinate interplanetary shipping. In effect, the Jovian system could become a hive of activity, with special suits for high radiation zones, exoskeletons to manage the lower gravity, and a swirl of scientific, commercial, and exploratory tasks. Whether extracting water for hydrogen fuel or building massive telescopes on the far side of these moons, the region's challenges are matched by the richness of resources and discoveries awaiting those intrepid enough to weather cosmic storms. Saturn, ringed with breathtaking arcs of ice and rock, similarly becomes a gateway to its own cluster of worlds. Titan, larger than Mercury, stands out with a dense nitrogen atmosphere and seas of liquid methane or ethane. Humans could potentially walk on Titan in lightly pressurized suits if they manage the frigid -180 degrees Celsius temperature, though the thick haze shrouds sunlight, demanding nuclear or other forms of energy. Methane and other hydrocarbons might be harvested as fuel or used in chemical processes. Meanwhile, Enceladus, though smaller, spews geysers of water from its southern polar region, implying a liquid ocean below the ice. A station on Enceladus might harness these plumes, collecting water for both life support and rocket propellant while studying whether that hidden ocean is an incubator for microbes. Over decades, an extended Saturn system colony might maintain trade routes in water, methane, and exotic chemicals, shipping them inward to Mars or outward to Neptune. Life on these moons remains a precarious balance of advanced suits, radiation shielding, partial to zero atmosphere, and reliance on geothermal or nuclear power. Yet with each new settlement, humankind's cosmic tapestry grows more colorful, a mosaic of cultures shaped by the unique gravitational pulls and aesthetic wonders of the Saturnian realm. Beyond Saturn, Uranus and Neptune preside over the kingdom of ice giants, each offering extreme weather systems, ferocious winds, and mesmerizing shades of blue. Uranus's 98-degree axial tilt creates bizarre seasonal swings lasting decades, while Neptune hosts winds surpassing 2,000 kilometers per hour, some of the fastest in the solar system. Both have faint ring systems and retinues of icy moons. Engineers might propose floating aerostat colonies in Uranus's upper atmosphere, using advanced materials that withstand ammonia-laced storms or lightning-laced hydrogen layers. Others might prefer constructing deep bunkers in the thick ice of a major moon, harnessing nuclear reactors to supply heat and light. Neptune's largest moon, Triton, believed to be a captured Kuiper Belt object, shows evidence of cryovolcanic plumes. A research base there could operate near these nitrogen geysers, sampling the planet's internal composition. With so little solar flux, nuclear or fusion energy would be a staple. The landscape would be one of perpetual twilight, with the distant sun providing a small fraction of Earth's daylight. Sub-zero wind storms could tear unreinforced structures apart, so every building, every vehicle, would be anchored or designed to fold away from the gales. Surviving these extremes demands that colonists are resourceful, with suits that can handle near cryogenic conditions and manipulate or store heat effectively for day-to-day tasks. Over centuries, these outposts might become stepping stones for beyond Pluto voyages, bridging the gap between the inner worlds and the Kuiper Belt. Pluto, demoted from planet status in 2006, remains a world of endless fascination. New Horizons flyby revealed a dynamic surface, including the iconic heart-shaped Tombaugh Regio, ice mountains, and possible signs of ongoing geological processes. Temperatures near -239 degrees Celsius and a tenuous nitrogen atmosphere underscore how precarious life would be there. Yet a hardy band of scientists and adventurers might carve out a settlement in a partially shielded cavern beneath the nitrogen ice. Nuclear or radioisotope thermoelectric generators provide precious warmth. Water ice or ammonia compounds can be refined for life support. Every breath, every drop of water is meticulously recycled, since resupply from Earth is measured in years of transit time. Communication signals to Earth, traveling at light speed, still need over 4.5 hours for a one-way trip, making real-time conversation impossible. Over time, a small group could adapt to the near-zero gravity environment by adopting new forms of exercise, possibly microgravity parks, where swirl-like sports develop. Their children might only know Earth from pictures or VR illusions, while Pluto's distant, faint sun becomes a symbol of how far the human frontier can extend. Should these settlers succeed, they become watchkeepers of the Kuiper Belt, forging links with missions that press yet farther into the darkness. But even Pluto is just an outpost at the edge of our sun's influence. Beyond lies the interstellar ocean, where cosmic radiation intensifies and solar wind recedes into the background. If we dream of bridging the 4.24 light-year gap to Proxima Centauri, home to at least one confirmed exoplanet in its habitable zone, our conventional propulsion methods, tens of kilometers per second, would take tens of thousands of years. This timescale leads us to generation ships or cryogenic sleepers. A generation ship is effectively a world unto itself, with closed-loop ecosystems that recycle air, water, and nutrients for hundreds of years. Astronauts aboard might become multi-generational dwellers, many born in transit, living out entire lifespans inside rotating cylinders that simulate gravity. Shielding could take the form of thick shells of ice, plastics, or magnetically generated fields. Some designs propose Ram's-coupe starships that collect interstellar hydrogen for fusion, while others propose advanced antimatter rockets or exotic warp drives. At these conceptual frontiers, biology and technology merge in new ways. Some might incorporate CRISPR-like gene editing to boost radiation repair or even integrate partial hibernation to slow aging. Societal structures could evolve so drastically that, upon arrival at the destination star, the traveler's descendants might have values and customs unrecognizable to the original Earthbound planners. In a yet more distant leap, we consider intergalactic voyages. The Milky Way is just one galaxy among billions in the observable universe, each harboring countless stars. To cross the gulf between galaxies, millions of light-years, exceeds all present comprehension. It might demand stable wormholes kept open by exotic matter, or warp drives harnessing energies at cosmic scales. The radiation in intergalactic space is severe, with cosmic rays traveling unimpeded across light millions of emptiness. A starship venturing there might rely on entire city-like arcs with power drawn from advanced black hole reactors or zero-point energy concepts. Over possibly millennia, the crew's biology might morph drastically, with cybernetic limbs, neural implants that handle data flows, or partial assimilation into AI networks. Some might question whether these travelers remain human in a classical sense or represent a branching path in post-human evolution. They might anchor to rogue planets adrift in the void, capturing minimal starlight, or harness high-energy events like quasars and gamma-ray bursts. The further outward we go, the more pressing survival becomes, overshadowing all comforts and illusions of normalcy. Such long-haul survival also demands we think about the suits and technologies bridging each environment. How do we craft an adaptive survival suit that works equally well on Venus's scorching surface, Mars's thin air, or the vacuum of space? We might incorporate hydrogen-rich layers to block protons, shape memory exoskeletons that anchor bone and muscle under partial gravity, or integrated AI that monitors metabolic functions and local hazards. Some might desire gene modifications borrowed from. As we near the conclusion of this sweeping narrative, it's clear that each new planet or cosmic environment we've highlighted demands unique strategies for survival. Surviving on Venus means conquering the worst greenhouse effect and unimaginable surface pressures, requiring robust thermal regulation and acid-proof enclosures. Living on Mercury requires dancing between inferno and ice, harnessing near-constant solar flux for power while ensuring meltdown or freeze-out never occur. Colonizing Mars merges engineering constraints, radiation, dust storms, partial gravity, resource scarcity, into a blueprint for the first truly off-world human city, one that might flourish under the surface or within geodesic domes. The outer system's gas giant moons, with hidden oceans and radiation belts, hold breathtaking potential for discovering alien life, forging new economies, and establishing scientific outposts on ice. The ringed glories of Saturn, the remote wonders of Uranus and Neptune, and the lonely hush of Pluto push the boundaries further, demanding advanced nuclear or fusion energy to keep the lights on and the water liquid. Then, beyond that, the starry ocean of interstellar space beckons, the final proving ground of multi-generational voyages, cosmic rays at full fury, and unimaginable distances that require us to become either stasis-bound or generational societies afloat in the void. Perhaps a million years from now, some offshoot of humanity might cross into the domain between galaxies, bridging unimaginable emptiness with a living starship that merges biology, AI, and advanced physics in ways that defy 21st century logic. In that ultimate scenario, survival is more than staying alive physically. It becomes about preserving culture, memory, and the intangible essence of being human. Could an intergalactic arc carry entire libraries of Earth's languages, arts, philosophies, and comedic sketches? Would they adapt them into new hybrid forms shaped by centuries of introspection under alien suns? How might the inhabitants cope with the existential weight of drifting through darkness for centuries at a time? Tied to that is a sense of wonder. Each new environment might become the seed of a fresh narrative, a new human myth born of luminescent seas on Europa or the purple twilight above Titan's methane lakes. Over cosmic timescales, multiple offshoots of humanity might diverge radically, shaping the galaxy and beyond in ways no single blueprint can predict. Thank you for embarking on this expansive intellectual journey, a reflection that merges real scientific facts, forward-thinking technology, and the ever-renewed power of human imagination. If these vistas spark your excitement, if they invite you to imagine how you might design a survival suit for Mercury's Terminator or a floating city in Venus's upper atmosphere, then do share your thoughts, like this deep exploration, and subscribe to sustain the community of cosmic dreamers. From the vantage point of Earth, still our cradle, we look upon the heavens with awe. But perhaps not so long from now, people might watch Earth from the vantage of an alien sunrise, forging a new story of survival, adaptation, and exploration that only grows richer with every leap we take across the cosmic sea.